And then we've got the properties of exponents that you've hopefully are familiar with. You can kind of review those if you need to. And let's start the problems. Okay, so let's finally answer that question. How do we differentiate 2 to the x with respect to x? Scroll down here. So I want to do the derivative of 2 to the x. I'm going to start by rewriting 2 to the x in base e. So this is kind of the prep step. I'm rewriting my what I'm differentiating, the function I'm differentiating. So I'm doing the derivative of e to the ln 2 x. Okay. And let me remind you that ln2, I'm writing it in parentheses there just to remind you that ln2 is just like a self-contained number. It's a constant. So just imagine that it was just a 2 or a 5 or a 10 or something. So it's like e to the 10x or e some constant times x. The constant just happens to be written in this weird way, ln2. Okay, so just kind of get used to that. And the technique we're going to have to use on this is the chain rules, because we've got our inner function here, and the outer function is the exponential. So our u will be ln2 times x. That's the inner function. The outer function will be e to the u. Chain rule says we do the derivative of the inner times the derivative of the outer. So derivative of the inner with respect to x. It's a constant times x, so the derivative is just the constant, right? If it was 5x, the derivative would be 5. It's ln2x, the derivative is ln2. And dy du, the derivative of the outer, is just e to the u, right? And that's what makes the e base convenient, right? It's its own derivative, okay? So dy dx is just derivative of the inner, which is ln2, times the derivative of the outer, e to the u. And the last thing I want to do is actually replace the u. U substitution is what it's called, but you've got to substitute it back, right? You've got to put it back. So u was ln2 x. Okay? So the technique we used here is we had a base other than e. We converted it to base e, and then used the chain rule. And that's how I would recommend doing it. But if you compare our answer, there's kind of patterns that emerge if you do enough of these. And if it had been the derivative, wait, oh. Okay. This is the derivative of 2 to the x, ln2 e to the ln2 x. If it had been the derivative of 3 to the x, it would have been ln3 e to the ln3x, and so on. So if you look, they've written this out as a formula. The derivative of any number a to the x with respect to x, ln a times a to the x. Where does that a to the x come from? Oh, well, I forgot to do one last step. They take this, and this is what I've written is correct, but this, remember, was 2x. So it will look a little nicer if I write that as ln2 times, put it back in the original base it was. I forgot to do that. Whoops. But there it is, ln2 times 2 to the x. And so the derivative of 5 to the x would be ln5 times 5 to the x, right? And that's what this little differentiation formula is telling you. You can use that formula if you memorize it, or you can just use the chain rule. I'd recommend using the chain rule because it's less to memorize. Okay. Well, what if we have sort of, it's not just 2 to the x, but 2 to the, say, 3x. There's a couple ways to approach this. I'll do it down here. Derivative x of 2 raised to the 3x power. I'm first going to rewrite my 2 as e to some power like I did in the other one. Write that as e to the ln 2, right? That's what 2 is. And this is raised to the 3x. Remember, ln 2 is just a constant. And remember the rules of exponents. I can, if I have an exponent raised to another exponent, I can just multiply the two. So this becomes e to the ln 2 times 3x. I'm always careful to write the ln 2 in parentheses so that it doesn't look like the 3x is inside the ln, because it's not. ln 2 is just, again, like a self-contained number. Just think of it like a 5 or something like that. So now when we go to do our chain rule, similar to before, but what we've got as our inner function is ln 2 times 3x. ln 2 times 3 is just some number. That's just a constant. So it's still just a constant times x. So the derivative of the inner, du dx, is just the constant, which is ln 2 times 3. It might be better to write that. Well, no, we'll leave it like that. But the 3 is not inside the ln. Just keep that in mind. And our y, if u is that, then y is just e to the u, dy du. Again, e to the u is its own derivative, so that's convenient. And this derivative will be the derivative of the inner times the derivative of the outer. That's from the chain rule. So ln 2 times 3 times e to the u. It's the derivative of the outer, derivative of the inner. Replace my u. So ln 2 times 3 times e to the ln 2 3x. That's what u is. And I'm not going to forget the step I forgot last time, which is to take this, which looks kind of ugly, and realize that that is the same as this, which was originally written in a nicer looking way, which was 2 to the 3x. So answer is ln 2 times 3 times 2 to the 3x. Okay. Let's see. Yeah, and notice that what we end up with when we did the derivative of 2 to the 3x, we ended up with ln 2 times this 3, and the 3 is just the derivative of the inner. It's just du dx, right? And then times the original, what we started off with. So that's all just from the chain rule. And if you look at the way they sort of generalize that, yeah, I'll try to compare it. Okay, so you can see both of those, but they say in general, if we have a base other than e, so like a to the u, we've got some function in there. We're differentiating that with respect to x. It's going to be ln a times a to the u times du dx. Here's ln a. There's our a to the u. There's our du dx. Okay, you can use this formula, but to be honest, I think it's easier just to use the chain rule rather than to rely on these formulas, which I'm not going to give you anyway. So.